Today we're going to identify tangents. And the tangents we're going to talk about with circle is not the same type of tangent that we talked about when we talked about trig ratios. Tangent is a name for a line in a circle, not trying to find missing sides of triangles. Secants, you'll see the word secant for those of you that eventually go on to trig. You'll see the word secant again. It won't be in the same respect of talking about a circle, though it could, but you'll talk about it more involving trig ratios there. And chords, not the music chords, chords, again, in a circle. And using properties of tangents to solve problems. Tangents are going to be the main thing that we focus on today, although you are going to learn the other terminology. So, pretty easy. We've identified all of these parts every time we've talked about anything. Very first time we talked about interior and exterior angles, points in the interior, points in the exterior. Then we talked about interior and exterior points in triangles. Then we talked about interior and exterior points in polygons. And now we're going to talk about interior and exterior points in circles. So the interior of a circle is the set of all points inside a circle. So if I had a point and I graphed it anywhere inside the circle, we would consider that in the interior. So just the opposite, the exterior of the circle is the set of all points outside the circle. So if I took a point and graphed it outside the circle, it would be in the exterior of the circle. A chord. A chord is a segment whose endpoints lie on a circle. So if I had a line and its endpoints stopped and touched at two different points on the circle, that line would be called a chord. So we might say that this is point A and this is point B. So AB would be a chord. Now take special note of the fact that this tells you that a chord is a segment. And this will be going back to what we talked about that very first day that we spent geometry class. Actually the second day, because the first day it was, hi, how are you? This is who I am. This is who you are. Nice to meet you. Then the second day we actually dove into geometry. We talked about segments and lines and the difference between them. So a chord is a segment. Then, a secant is a line that intersects a circle at 2 points. So remember, a line extends in opposite directions forever. So that blue line is a secant. Okay, now, where the line crosses our circle at 2 different points, those may be named, or you may see this named as line L. Okay, it may be named both ways. Keep in mind that our secant that we labeled here, if the points where the line meets the circle are labeled, we could also call this chord CD. It could also be a chord. If it's named with just an L, we don't have 2 points to name it by, so then it would just be a secant. A chord and a secant can also act as the diameter of our circle. It could also be the diameter. And that's kind of drawing on some prior knowledge that you guys have. about circles. And then our last term that we talked about, a tangent. Tangent is also a line, so it extends forever in each direction, in the same plane as the circle that intersects at exactly one point. So that line only intersects the circle at one point. So this line here is our tangent. And as I said before, tangent lines and the word tangent we're really going to focus on today. Then, we said that the tangent crosses the circle, it meets the circle in exactly one point. So I highlighted that point for you, and that's what this arrow is pointed to. And the point where the tangent and the circle intersect is called the point of tangency. So that point is our point of tangency. Okay, a lot of new vocabulary, I know. But these vocabulary words are going to be important to know. Any questions so far? No, because this line crosses in multiple points. It meets at A and B. It only applies to the tangent line. And it's the point where that tangent line meets the circle. So if you have a chord or a secant, you wouldn't have a point of tangency. Okay, so here we have a circle. And this says identify each line or segment that passes through circle P. Now, when we name a circle, we name it by showing the circle symbol, and we put a little dot in the middle, and we put the center of the circle in there so that it doesn't look like you write OP, because then it looks like you're naming a line. So that's why we put the little dot in the middle. Somebody asked that earlier. So this is circle, and we name it by its center point. So the center of this circle was circle P. Makes it circle P. Okay, this center point was X, it would be circle X. So this says identify each line or segment that passes through circle P. First, we're going to focus on the three that we had talked about, and then we're going to also talk about the diameter and the radii, because they're also lines or segments that fall within the circle. Radii is the plural form of radius. Okay, so the first one we identified on the page before were chords. And recall that chords are segments whose endpoints lie on the circle. So they're segments. So one of our chords would be QR. One of our chords would be QR. And because it's a segment, we label it as such. And remember that segments are named with just a line drawn over top of them. We also have another chord. And we also have another chord. This line here has points S and T labeled. So we can say that that's chord ST. Okay, second type of line we talked about was a secant. And we said that secants are lines, so something that extends forever in each direction, that passes through the circle in 2 points. So again, looking at ST, it's a line as noted by the arrows that point in each direction. So ST is also a secant. But when I name it as a line. So we have arrows at both ends of our line over top. UV would not be 1 because it's a line, because it doesn't intersect the circle in 2 points. But UV would be our tangent line, because it's a line that intersects the circle at only 1 point. Okay, ST couldn't be a tangent because it intersects twice, but UV only intersects once at point U. Okay, and although this doesn't ask us to identify the point of tangency, point U would be our point of tangency. Because that's where our tangent line meets the circle. And like I said, in circles, we also have the diameter. The diameter is a line that passes through the circle. So what's the, oh, wow. I should not talk and write at the same time. Diameter. So what's the diameter of this circle? ST. Diameter extends through the center from one side of the circle to the other. So ST would be it, and ST is a segment. Because remember that the diameter doesn't continue to extend past the circle. It's only identified inside the circle. So it's just segment ST. And as we discussed, radii is the plural form of radius. And we actually have 3 radii in this circle. When we name the radii, we start with the center point. So we're going to start with P in all 3 of these. I'm going to overlap a little bit here. So what's one of the radii? PQ. PQ, right there's one of them. They're also a segment because it ends at the circle's edge. What's another one? PT. And that means the last one's going to be PS. So keep in mind that these are all, other than point of tangency, because that's a point, not a line or a segment, these are all lines or segments that could show up inside a circle. You're going to have something like that today on your classwork, where you're going to have to identify all the lines and segments that are within each circle. Okay, and then on this page, I'm going to have to draw some stuff in because my center points disappeared. That's close enough. Okay, this page has diagrams of 2 circles and how they relate to each other. And I should have made cards so that I could actually show you. Maybe what I'll do. I don't have any in there. Okay, say I held a piece of paper up with a 3, 4, 5 right triangle drawn on it. And then in the other hand, I held a piece of paper with a 3, 4, 5 right triangle drawn on it. And I ask you guys to tell me how I would relate, the word I would use to describe the 2 triangles' relation to each other. Remember, right hand, 3, 4, 5 right triangle. Left hand, 3, 4, 5 right triangle. What word would I use to describe their relationship? Not supplementary, that's 2 angles that add together equal 180. Not similar, because remember similar is where we have like a smaller one, but it's the same as the larger one. Congruent. Congruent. When they're exactly the same image, they're considered congruent. So if 2 circles have congruent radii, so in this circle, this radius is 6 inches. In this circle, this radius is 6 inches. I would consider them congruent circles. It means that the circles are exactly the same. So two circles are congruent circles if and only if, that biconditional again, if and only if they have congruent radii. Would also be true if they had a congruent diameter, because a congruent diameter would also mean that they have congruent radii. Okay, then in the second image we have two circles, one inside the other, and they share the same center point. So in the smaller circle, the radius might be 6 inches, and considering I just copied this image and put it down here, it would be. And then the outside circle may have a radius of 7 inches, but they share the same center point. We call those concentric circles. Okay, so if I gave you a pop quiz tomorrow, gave you a compass and said, draw me a set of concentric circles, you would use the compass to draw a circle, push the point either in or out, and draw another circle from the same center point. You would not move where the point of the compass sat, where the sharp point of the compass sat on your paper. Okay, then, and this is going to go back to that tangent word we talked about. I told you it'll show up a lot today. Two coplanar circles that intersect at exactly one point. So in this diagram, we have that the circles intersect right here. And it's the only point that they meet. Although it does look like they may meet somewhere else. It's just the way that the circles are drawn. From this point, the inner circle progressively gets farther away from the outer circle. Over here, that's the only point that they meet. Okay, so two coplanar circles that intersect at exactly one point are called tangent circles. Okay, and then for all intents and purposes, for those of you that care, these, when you have one circle that's inside another circle and they intersect at one point, these are called interior tangent circles. One circle is inside the other. So here, where the only point that they meet or lie within one another at the point that they meet, these would be exterior tangent circles. Okay, and then that point where they meet, that's also still considered a point of tangency. Because I could draw now a single line that touches both those circles in only one point. Same thing over here. I can draw one line that touches those circles in exactly one point. Point of tangency. We're going to use that here in the next problem. So example 1.1, identifying tangents of circles. Part A just wants us to find the radius of each circle. So we have two circles. A is our larger circle. Remember, we name it by the center point. B is our smaller circle. So we have circle A, circle B. Okay, now, when circles lie on a coordinate plane, it's really nice to be able to figure out their radius. Okay, because remember, a radius just extends. It's the same distance from point A, no matter which direction I extend the radius. So in a coordinate plane, if I extend it either vertically or horizontally, all I then have to do is count the number of blocks. And that'll give me my radius. So here I'm just going to extend the radius up from A. So I extend the radius up from A. So starting from point A, where that's 0, I moved 1, 2, 3, 4 blocks. If I extended it in this direction, which is kind of already drawn in there for us, it would be the same thing. 1, 2, 3, 4. So no matter which direction you extend it, it's still going to give you the same answer because the center is the same distance away. And I'm going to say that it's 4 units because we weren't given a label. We weren't given whether it's centimeters, meters, whatever it may be. So A is 4 units. Then I do the same thing for B. Draw my radius in there, say, okay, 1, 2. Same thing all the way around. So B's radius would be 2 units.
So what you did for A, you just counted up, right?
Mm-hmm. Yeah, you could also count down or left or right till you got to the edge of circle A. But I just extended it up because it was easiest for me. Okay, then part B says identify the point of tangency, so where the two circles meet, as well as where the tangent line meets those two circles, and write the equation of the tangent line at this point. So it wants us to identify where this point lies. That's going to be our point of tangency. And it wants us to give an equation for this line. Okay, so when we name the point of tangency in the coordinate plane, we name it as an ordered pair. So we want to name it x, y. Okay, also remember, and we identify that our point of tangency is right here. It's the point where our two circles meet, as well as this line meets the circles. On your test, some of you graphed your points incorrectly. Remember that an ordered pair is x, y. Some of you graphed up or down first, and then left or right. And I don't know if it's because we get slope confused with graphing points, but we move left or right first because we move along x-axis first, and then we move along the y-axis. And I know that you guys have heard me say several times this year, but when we graph a point, we walk to the elevator before we ride it up or down. Okay, so our point is right here. We start from the origin, which I know with the circles there it's a little hard to see. Starting from the origin, we walk right 1, 2, 3 places. And we don't have to ride the elevator anywhere. Our point's right there. So our point is at 3, 0. Our point's at 3, 0. X-axis is 3. Y-axis is 0. We didn't move anywhere. Next thing it asks us for is the equation of the line. And there's 2 important things to remember when we're doing the equations of the lines. Okay, you guys are used to seeing one that's like this, so that we find the slope, and then we find a point, we plug the point back in, and we find the equation. Well, notice that our point of tangent, or that our tangent line is vertical. If we have a vertical line, then the equation of our line will take the form of x equals. Okay, so if our line is vertical, the equation of our line is going to be x equals. And I know that this is stuff that you guys tend to get confused with. If it's a horizontal line, I have not been able to spell horizontal all day. Then it takes the form of y equals. Okay, and the reason why I think you guys get this confused is this is vertical, so we're going to say that x equals something here, but this line runs the same way as the y-axis does. The equations run perpendicular to their axis. So I just told you this line was vertical. So our equation is going to take the form of x equals. So we'd say, okay, well, at this point, x would equal 3. Because we have 1, 2, x is 3. So the equation of our line is equals 3. And all this means is that for every value of y, if I told you that y was 1, x would be 3. If I told you y was negative 6, x would still be 3. So all those points would fall along that line.
But how do you know it's come down that far? All I'm saying, like,
All you have to do is just draw a vertical line that extends forever in each direction. It doesn't matter how far you go down, as long as, for the tangent line, you draw arrows at each end.
so you just count over how far it goes, right?
Hmm?
Just go over how far it goes, right?
Yeah. Okay, guys, also notice here. Also notice, this ordered pair is xy. X is our, 3 is our x value, 0 is our y value. Equation of our line is x equals. Take your x value and plug it in here.
So that'll always be your x.
That'll always be your x. Now, if it was y equals, we would take our y term and plug it in. Okay, so let's try another example of this. Let's try another example. So here we have circle C and circle D. Circle C. Amber, what's circle C's radius? 1. Circle C's radius is 1 unit. Circle D. Take your center point and extend it out to your side. So C's radius would be what, Trey? Or sorry, D's radius would be what, Trey? 3. 3 units. Okay, so again, that's all we have to do for part A. Identify the point of tangency. Okay, so the point of tangency is where our circles meet. So it's the point where our two circles meet, and we're able to draw a tangent line so that it only intersects with each circle once. So what point would our point of tangency be at, Daniel? Yeah, what coordinates? 2, -1. Okay, 2, -1. Remember x, y? Okay, now, our tangent line that they drew in for us. Tangent line that they drew in for us, is it horizontal or is it vertical?
Vertical? I don't know.
Horizontal. The horizon, when you're standing like on top of the mountain, you're looking out at the horizon. It's flat. Okay, so if the line is flat, it's horizontal. If it goes up and down, it's vertical. Okay, so it's horizontal. So what form is our equation going to take? Y equals. So y equals -1. Okay, and this means for every value of x, y equals -1. So if I told you x was 4, you'd still just go down -1, and that would be your point. So every point would fall along this line. Same trick that I just showed you on the last slide. If the line's horizontal, and we're going to say y equals, take your y coordinate, plug it in. Take your y coordinate and plug it in. Okay, one other thing I want to show you. is if we have two circles that are separated from each other, and we draw a tangent line to both of those circles. This would be known as a common tangent. Because circle A and circle B have the same tangent line in common. If it's something like this, where our tangent lines are drawn outside of our circles, notice that this is at the top, this is along the top, this is along the bottom, this is along the bottom. This is known as an exterior tangent. And if we have a tangent like over here where tangent P is like along the top of circle A but along the bottom of circle B, this is known as an interior common tangent. Because it crosses over the interior between those two circles. Any questions so far? We're getting into the last part of the lesson. Now, this information that we're going to learn right here is probably one of the most important pieces of information you can take from this lesson. I've been doing a lot of SOL remediation here in the last week or so, and we've been reviewing a lot of problems about circles and three-dimensional figures. And a lot of the circle questions that have been coming up have to deal with information exactly like you see right here. So if two segments are tangent from the same external point, so here I'm going to tell you that we have point A that lies outside the circle, an external point. Okay, and we have two tangents drawn from it. First one is tangent AB. Notice that it intersects the circle at only one point. We have tangent AC. And I didn't draw that very good, but it only crosses the circle at point C. But because it passes through the same external point, we can say that the two segments are congruent. So AB has the same length as AC, as shown over here. AB is congruent to AC. Because they're both tangent lines to the same external point. So if you see two tangent lines that pass through the same external point, you automatically know that their two segments are congruent. So here we have common external point, H, and it tells us that HK and HD are tangent. So as soon as we see that they're tangent, we can say that HG is equal to HK. And from here, we'll do the same thing we've done with every problem we've set to equal to each other all year. So HG, we're going to substitute in 4 plus 2a. HK, we're going to substitute in 5a minus 32. We're going to solve the equation. So Jennifer, what's the first thing you want to do? Subtract 2a from both sides. So that gives us 4 equals 3a minus 32. What's the next thing you want to do? Nathan? Add 32 to both sides. Kind of running out of space here. So we add 32 to both sides. When we do that, we get 36 equals 3a. Denzel, what's the last thing we want to do? Divide by 3. So we get A equals 12. Now the problem wanted us to find HG. So we're going to take the answer that we found in for A, and we're going to plug it back into HG's equation, which was 4 plus 2A. So we get 4 plus 2 times 12. Four plus 24. 4 plus 24 is 28. So HG equals 28. And if I want to check my answer, I could plug 12 into this equation. 5 times 12 is 60. 60 minus 2 is 28. We said that these two were equal, so that checks out. That helps us check our answer. Okay, any questions so far? Let's try another one then. I moved my... Okay, RS and RT are tangent to circle Q. So you have circle Q, and it says that RS and RT are tangent circles, or are tangent lines. So if they're tangent to each other, what can I say about RS and RT? That they're equal to each other. So RS equals RT. Joseph, what am I going to substitute in for RS? X over 4. Gary, what am I going to substitute in for RT? X minus 6.3. Okay, now, can anybody volunteer what they think we're going to do first to solve for this problem? Daniel. Multiply by the opposite reciprocal. Well, you could say that. Multiply it by 4. You could also say 4 over 1 if it makes it easier for you. So I'll write it that way over here. On this side, I'll just write 4, since it's the same thing. Here, the 4's cancel out. We're left with X. On the other side, take notes to the fact that I put the entire quantity that we had on the right-hand side inside parentheses, because I have to multiply 4 by both parts. So I have 4 times x, which is 4x, and 4 times negative 6.3, which gives me what? 25.2. That's okay. So Ryan, what do I want to do first? What do I want to do first with this equation? Now we're not going to divide by 4. That'll put us right back to where we were at before. We're going to subtract 4x from both sides. This sign goes with this number. So this is actually positive 4x. Okay, so we get negative 3x equals negative 25.2. Keaton, what am I going to do now? We're going to divide by 2. Negative 3. We need to get rid of this sign too. X needs to be positive. So negative 3's cancel out. Negative 25.2 divided by negative 3. What do I get? It shouldn't be 17.4. 8.4. Okay, so we get x equals 8.4. This wanted us to solve for RS. So RS was originally x divided by 4. So we take x and plug it back in. So we have 8.4 divided by 4. What do we get as our final answer? 2.1. Okay, that took a little bit of a different approach, but we were still able to solve it. Okay, last one. Same setup. RS and RT are tangent to circle Q. So that means RS equals RT. Substitute in what we know. RS equals n plus 3. RT equals 2n minus 1. Caitlin, what's the first thing I want to do to solve this? Subtract 3 from both sides. Okay, so I get n equals 2n minus 4. Abby, what do I want to do next? Subtract 2n from both sides. So we get negative n equals negative 4. Well, I don't want n to be negative, so what can I divide both sides by to change the sign? Negative 1. Like I said, that'll just change the sign on both sides. So we get n equals 4. N equals 4. Again, this one wants us to solve for RS. So RS was originally n plus 3. Substitute 4 in. We get that RS equals 7. If we plug 4 back into the other equation, 2 times 4 is 8, minus 1 is 7, so we still get the same answer. Okay, any questions on this? Okay. Then, classwork, 751, 4, 6, 10, 12, 14, and 16.